Hi everyone and welcome to a new video about BJT amplifiers. This is our second example. In this example we will again look at the NPN transistor circuit, and specifically we will look at the effect of the emitter resistor. And this resistor is shown here in red, and that resistor will really give a stable amplification for the circuit. We will see that in our discussion. Of course, we will work out everything in our calculation step by step and also verify these in SPICE simulations. So let's look at our problem. We have this circuit given. You see the AC voltage source. We have also the source resistor, RS, and we have a capacitor which will then decouple this source here. We have the sources, the VCC, 1 DC voltage source. For the transistor we have again 0.7 volts for this part, and we have the resistors. The values are shown here. We would like to calculate the voltage gain, which is from the output, the collector node, to the input, Vi, if the beta of the transistor is 100. And then we repeat the process. Then for the beta is 200, so the parameter of the transistor has changed enormously from 100 to 200. And then the second, another change is question C, is that it is now 300. And we will see and compare that in the final discussion what the effect is of this change in beta. Okay, we assume of course in our discussion that the transistor, the BJT, is in linear region of operation, so the IC, the collector current, is equal to the beta times the base current. Okay. So the solutions. So first we start for our amplification example with a DC analysis. Now for DC analysis you consider the capacitors, all capacitors, as a perfect open circuit. So this part of the circuit is then disconnected. So you have only this part of the circuit. So you have actually this part, and you can see that everything is now in capital letters given. So I see the collector current, the base current, and emitter current, and everything also for voltages. So we will now further analyze this to determine the DC quantities. Now first we need to transform this part of the input to the Thevenin equivalent circuit, which is shown here, and that is then the VTH, voltage of the Thevenin, and the resistor of the Thevenin equivalent circuit, this part. So how to determine that? Now for that we go to the Thevenin equivalent circuit at node B, which is the same node here. So we will do then the following. The Thevenin resistance is just the parallel combination of the R1 and R2 looking back in the base. That is then R1 in parallel with R2, and if you do the math here you will get 8 kilo ohms for our Thevenin. Now V Thevenin, the voltage of Thevenin, is then the voltage divider here, just looking at node B, R2 over R1 plus R2 times VCC. Now if you now do the math you will get here 3 volts. Okay, these are important parameters because now we can use this circuit having these two values to calculate the IB and the rest of the parameters. So the Kirchhoff's voltage law at the input load, this one, will then allow us to write down VTH is equal to RTH times IB, and then this voltage, VBE, times the RE plus RB times IE. That's actually shown here. But we know that emitter current is given by the beta plus 1 times the base current. So we can now take them together and substitute this emitter current in here. And we have this equation. Now you can see that the equation now has only one unknown, which is the base current. Now we can collect them together, and we have now a coefficient for base current. And now you can even have an expression for the base current in terms of the rest of the parameters. These are all known because you know the Thevenin voltage, you know the VBE, you know the Thevenin resistance, and you also know the RE and also the beta. So this can be calculated for specific beta and other parameters in our circuit. So let's now look at it and moving on further for the beta as 100, the first case. If you now use the base current expression here and then substitute everything we have for beta as 100, you will get 25.9 microamps. Now, if I now use the linear region of operation condition, then I can use this formula for the collector current. This is here, and that will be then give us the 2.59 milliamps. In a similar case, the emitter current can be calculated, and it will give us 2.62 milliamps. So we have now the three currents, the DC currents for the transistor circuit. Now, moving on and then using this circuit, and then specifically the collector emitter voltage, VCE, we can set up this equation. You see the VCC is equal to the collector resistors times the collector current plus the VCE plus this voltage here, which is then IE times RE, which is shown here. Now express this VCE in terms of the rest of the parameters and then substitute everything we have because we know the resistors, we also know the currents, and we have now 7.73 volts here. Okay, that's for this condition, and we move on with the AC analysis now using this DC information. This is the small signal model of this circuit, and specifically the dashed part here in red is that of the transistor, the BJT, and this is the most basic, most simple model. You see here a dynamic resistor here, R pi, we will use that shortly, and we see here a dependent current source, and it's called beta times IB. Everything is here in the AC parameters, so there are small letters and small subscripts. This base current here will be then multiplied by a beta, which is the exact same beta as we have here, and that will then produce here a AC collector current. This part is again only the transistor. Now you see the base node, the emitter node, and the collector node. In addition, you see the collector resistor here is directly connected to ground. Why? Because when you consider the AC analysis, the DC voltage sources are considered to be zero because there is no change in ideal DC voltage sources. So that's why we have here from the collector resistor to ground. Now the emitter is also going to ground from the emitter node, the resistors, and we also have the R1 and R2 also effectively to ground because this node will be then through R1 go to ground. So you have now a parallel combination effectively in the AC domain R1 of R2. Then you have the short circuit of capacitor C because that is also considered to be a perfect short for the AC analysis. And then we have the RS and then we have our AC input voltage. So that's how you set up the AC model of this circuit. Okay, let's bring them together. We have this IB required shortly. Okay, and we have this circuit. Well, let's move on and then first designate the two parameters, which is the impedance in the base, so ZIB, and we also have this, the ZI, which is then this input resistance or impedance at node B. So going in here or going in there, there are two parameters depending on how you look at your circuit. So ZIB is then equal to R pi plus this resistor multiplied by the beta plus 1. Why? Because the current going in here is IB, but current going in here is not IB, it is IE, which is the emitter current, but that is beta plus 1 times larger. So you see the resistor here, R pi, but this is then seen beta plus 1 times larger. That's why we have it there. But we don't know what R pi is, and that dynamic resistance is dependent on the base current, the DC voltage of that base current, and that is given by this formula. In here we have the VT, which is called the terminal voltage, and that has 26 millivolts value at approximately 300 Kelvin, let's say 27 degrees. Now if you now substitute the values in here, you will get for the R pi 1004 ohms, so approximately 1 kilo ohms. Now, if you now substitute the values in here, we know the beta, we know also the RE, which is 800. Now you will get for the ZIB the 81.8 kilo ohms. That's for this part of the impedance. In a similar case, we now know that this impedance here is parallel with this resistance here, which is then the parallel combination of R1 and R2. So we can move on and say ZI is equal to the parallel combination of these three parts, R1, R2, and ZIB. So I can move on and then write it down in this form. 1 over ZI is equal to 1 over R1 plus 1 over R2 plus 1 over RZB. Now, if I now substitute everything in here, we have 40K, 10K, and also the 81.8 kilo ohms for the ZIB. Now we can calculate the ZI as shown here, which is then approximately 7.29 kilo ohms. Okay, now we are now very close to our gain formula. This is the gain formula, voltage gain formula we have given, VO over VI. Well, in order to get the actual gain here, we can split the problem in two stages. We can go from the VI to the VB and then from VB to the VO. Now, in order to go from VI to VB, which is then VB over the VI, which is this part, and then from the VB to VO, which is then VO over VB, that is this part. So you split the problem in two fractions and then you multiply them, you will get the exact same result because you can now divide out the VBs and you'll get VO or VI. So mathematically that is correct. VB is just the voltage divider rule here because that is the ZI over the RS plus ZI, and that is just the voltage gain looking from here in this direction. But for the other one, for the VB, that is this voltage across R pi plus the voltage across RE, so that you will have then this expression. Now we also know what the VO is because this voltage here at this node, the collector, has this resistor RC times the negative of the IC because the current is flowing here from ground to the collector. It's circulating like this, but we measure from collector to ground, so we have a sign inversion. Again, this expression. Since IC is also beta times IB, we have this expression. Now, if I now collect this together and then make this fraction here, VO over VB, we have this. So we have now two parts of the voltage gain expression. Now moving on, we can now say IB and IB and IB, we can divide it out. We have this. Now then we get the following. We can set up and then write down everything, multiply the first and the second part, and now substitute everything in here for the specific case of beta of 100, and you will have this expression. If I now work it out, you will get approximately minus 2.29, very close to actually this value. So we have now our voltage gain. You also see that there's a sign inversion, so the output will be an inverted portion of the input voltage. Okay, that's for question A. Let's look at the DC analysis in the simulation results for specifically the beta is 100. This is the simulation circuit. You see the IB, IC, and IE, and also the VCE, and also the voltage at this node. This is an extra information. You see what we have calculated, and you see what we see in our simulator. So it is very close. This is 26.2 approximately. This is 25.9, and you see 2.63 approximately milliamps. That's also what we have approximately. So very close to what we have calculated. So that is verified for our DC analysis. Now moving on to the transient response, and we now like to know if the gain is correct. Now we have now an input voltage which is 10 millivolts peak, and we have a frequency of 10 kilohertz. That's the blue line. And the red line is the output. You can see it is inverted version. The maximum output voltage here is 9.773 volts and the minimum is 9.727 volts. So this is the input, and the peak input voltage is 20 millivolts because 10 up and 10 millivolts down. And you can see also the peak output voltage is again calculated using just the max and the minus the minimum. That is 46 millivolts. Now if you do now the simple mathematical operation, you see the minus the peak output divided by the peak input, you will get minus 2.3 volts. Now from the calculations we had minus 2.29, and from the simulator you get this. So you see that this is a very nice result and it verifies our calculations nicely. Okay, now we will now do the exact same procedure, a little bit faster than for the beta is 200. So moving on, an exact same procedure, but then everything stays the same except the beta is 200. So of course the base current will change, and then the collector current will change, and also the emitter current will change because the beta has changed from 100 to 200. Now in addition, you will see that the VCE is also changing, going to 7.36 volts. Now for the AC analysis, we still have the same model. So this is again the dash part for the transistors, and then getting them together again, we can say this part and this part is again what we like to calculate. But this R pi will now change because the IB has changed. Again using the same formula, but now the 13.6 microamps instead of 25.9 microamps we had for beta S100. So now you see it is now 1908 ohms. So it has increased almost by a factor of 2, in this case for the R pi. Now substitute this value in here, also the beta S200. Now you will have a larger value for the ZIB. Okay, now again the ZI here is then a parallel combination of R1, R2 and this resistor, or the impedance I must say, and then we have this expression, and then you substitute everything here and you will get now our new value of ZI. You see that is not really changed compared to the first case for beta S100. So we have now 7.63 kilo ohms. Now moving on the same format for our voltage gain, split the problem in two and then multiply that with a voltage division and then the VB and the VO, everything the same procedure, so I'll go a little bit faster. You see now that we have again using the split formula, but now we have a couple of changes. ZI is changed and also the R pi is changed and the beta, so we have 3 changes. Everything is actually the same, so the RS is the same, the RC is the same, RE is the same, only changes the Z pi, R pi, ZI and the beta. Now if you now calculate this again, interestingly we get to minus 2.31 instead of minus 2.29. So this difference is not very much. We make actually the change the beta from 100 to 200, that is 100% up. How much change do you see in your gain? Not that much. So very small change. That is sort of the bistable design due to that RE. If that RE was not there, which we had seen in our example number 1 of the amplifier, the gain will change enormously when the beta will change. So that is not really a handy circuit for our amplification. Now, moving on, looking at the DC analysis simulation result. This is the circuit again. Now the beta is 200 for this circuit, for this BJT. We have now this calculated, and looking at the simulation result, we see that this is indeed confirmed and close to what we have calculated. Now moving on to the simulation result for a transient response. Now this is the gain we have determined, calculated, and this is again the same input voltage of 10 millivolts peak and 10 kilohertz frequency. The blue is the input, the red is the output. You see now again, this is the voltage input expression, peak 20 millivolts, and for the output again we have 46 millivolts if you do the calculation from the maximum minus the minimum value. So that means again we have minus 2.3 as a gain. And that's again very close to what we have calculated. So that is again confirmed. Now the final one, looking at the beta, is 300. So the next case, again changing the beta only. So I also again go a little bit faster because this is all clear from the previous 2 discussions. So we have now the new collector and new emitter current, also because we have the new base current, but the collector and the emitter current are not changed that much, but the base current is the one that is really changing. Also the collector emitter voltage is not changed that much. Now going on to the AC analysis, this is then the model again this is the part of the BJT, and we will take now that together, and we have now our base current new one. So we have again our impedances here, and we will now again calculate the new R pi using the new DC base current. Now we see it is 2813 ohms. So again it has increased. So new value now will be for the ZIB, having of course a beta of 300, will be much larger. Now that will be then 243.6 kilo ohms. Now moving on to the ZI, which is this part of the impedance, or looking from this part, you have again the parallel combination of 3 components, and that will give us the ZI of 7.75 kilo ohms. So you see again, this is not really changed compared to the previous 2 cases for the beta. Okay, again the output voltage expressions, again dividing the problem in 2 sections, getting them together, and then we have now the VB over VI this and VO over VB this one. So we will multiply them together, and you will have this expression. You see only beta, R pi and the ZI has changed, and that will give us again very close to minus 2.31 as the gain. And that's also what we have seen for the question A and for B, and question A was minus 2.29. So all very close to what we have calculated before. Again, the bistable action of the emitter resistor here. Okay, Looking now at the simulation results for the beta is 100. First the DC analysis. Again, now the BJT here has a beta of 300 in his model. You see the base current, the collector and the emitter current, and also the collector and emitter voltage. What you see, what we have calculated is very close to what we see in our simulation, so that is also confirmed. Now moving on to the simulation results for the transient response. This is the gain, and this is again the plot. Blue is the input, the red is the output. Again, same input voltage. This is the expression, 10 millivolts peak, and then 10 to the power 4, so 10 kilohertz as the frequency. The peak value of the input voltage is 20 millivolts, but for the output, again, the maximum minus the minimum is again 46 millivolts. So that stays the same. So this changes, of course, the maximum and the minimum values, but the peak value, this distance, stays the same. So the gain will be then exactly, again, minus 2.3. So that doesn't change. And that is, again, in agreement we have what we have calculated. So let's now summarize the calculation results. These are the calculation results. You see the three questions. Beta is 100, 200, and 300. You see the base currents, collector, emitter currents, also collector, emitter voltages, and the gains. You see the base current changes enormously because the beta is changing, but the collector current, emitter current, and also the collector, emitter voltage, and also the gain, especially the voltage gain, stays very constant. So there is a stable design here due to that RE. Of course, the choice of R1 and R2 also very important, also the RC, but the dominant part of this stability is really the emitter resistor. Now, summary of the simulation result, it's actually shown here. First, the DC analysis. For the beta is 100, this for the beta is 200, and this for the beta is 300. You can see how the current is going here. Beta IB is actually decreasing, but the collector current is almost the same, and also for the emitter and for the collector emitter voltage. Now, looking also for the simulation result for the transient response, you see the input voltage is always the same, the blue one, but the red one has a peak value, which is always 46 millivolts. So you can see the gain is in each case minus 2.3 as a value. So we have seen in this example, also with emitter resistors, how this circuit can use this resistor as a stabilizing component in our voltage gain. If you decrease this resistor, for example, make it 500 or 400 or 200, of course the stability effect will reduce. So the larger this value, the more effect it has on the stability. Of course, if you make it larger, you will also lose gain. So there is an optimum, actually a sort of a fight between the stability and the amount of gain you can achieve with this circuit. Alright guys, this is for this example about the BJT amplifier and complete discussion with the effect of the beta for this BJT amplifier with the emitter resistor for stable voltage gain. If you have any questions about this circuit and discussion, please let me know. I will try to answer them as soon as possible. In the next example, we will consider the bypass capacitor across the resistor RE, so the emitter bypass capacitor, and also what kind of effect it has on our gain and other parameters. So stay tuned, and we will see each other in another video. Take care.